Good morning and welcome you all to this session of the course on fluid machine. Now, today in this session we will start the discussion on centrifugal pump. Now, at the beginning of this course we have recognized that pumps, compressors, fan blowers are the machines of that category where mechanical energy is being converted to the stored energy of the fluid. So, the output of these machines is in the form of the stored mechanical energy, and in pumps and compressors this stored mechanical energy comes in the form of static pressure, that means in the static head, while in fans and blowers they are in the form of kinetic head or the velocity of the fluid. Pumps are those machines which use liquid and mainly water as the working fluid, while the compressor use air. This we already recognized. Now, pump again can be of two types, one is radial flow, another is axial flow. Now, the radial flow pumps are known as centrifugal pumps. The word centrifugal comes from the fact that in any radial flow machine there is a change in the centrifugal head because of the change in the radial position of the fluid while it flows through the rotor of the machine. And for this change in centrifugal head, the fluid either gains or release static pressure or static head, depending upon whether it is a pump, compressor or a turbine. But the word centrifugal is not used in case of turbine, but in case of pump it is used. And at the same time, this was also recognized that in case of pumps or compressor, when it is a radial flow type, that means centrifugal one, the flow should be radially outward. This is because when it goes radially outward, at the outlet the centrifugal head is more because of the higher radial location as compared to that at the inlet. So, therefore, while the fluid flows through the runner, it gains in the centrifugal head and accordingly in the static head. So, therefore, it is always radially outward, while in case of a turbine it is radially inward. So, therefore, it is apparent that a centrifugal compressor is in general the reverse or converse of a Francis turbine. Okay. Now, before going to describe this pump force on the rotor vanes, rotor blades and all these things, we first discuss the pumping system in general. Now, the word pumping in a hydraulic system refers to the lift of water, static lift of water vertically, but in broad sense it is to develop static pressure, develop the or to build the energy in the fluid in the form of the static pressure, by virtue of which the fluid can be distributed over a distance through pipe network system or it can be lifted up. And first of all, we just try to understand this pumping system and the net head developed by a pump. Okay. For that, let us just see this picture. Here, this is a system, this is a centrifugal pump. Now, this is the there are two reservoirs. Here it is explained in terms of the water lifting from a lower reservoir to higher reservoir. This is a lower reservoir, this is the higher reservoir. The lower reservoir is usually known as sump, while this is the higher reservoir. Now, the liquid, for example, here we take water pump, now is there in the sump and it enters through this pipe, that is the inlet pipe, and it goes to the pump. This is the pump. Then pump imparts energy to the fluid, it acquires energy, and at the outlet the energy is mostly in the form of static pressure, by virtue of which it goes up and is discharged in the higher reservoir. Now, if we see the different points, representative points, if we designate and see the total energy per unit weight in terms of head, we give some representative points A, B, C, D, E and F and take this line as the datum, okay, and from the datum the free surface in the lower reservoir is at a height H A, okay, and this the difference in the free surface or the height, the elevation of the free surface of the upper reservoir or higher reservoir and the sum the lower reservoir is HS. These are the nomenclature. J2 is the vertical distance elevation from the datum of the discharge plane. That means the discharge plane of the pump is at a vertical distance J2 above the datum, and similarly the inlet to the pump here just after the flange is Z1 from the datum. And in this picture we show two pressure gauges, one is at the inlet to the pump, just at the inlet to the pump, which is recording the pressure, and this corresponding pressure it is P1 by rho g. The 1 subscript 1 is given at the inlet to the pump, and this is P2 by rho g, that is the pressure head at the outlet from the pump. The subscript 2 is given at the outlet from the pump. Now, if we draw a diagram like this, head versus the flow path, head versus the flow path, this is the head and this is the flow path. This is head, 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 and this is the flow path, flow path. So, we will see like this, if we start from the point A here, at a point A here, which has a head. Now, at A, the head is only, now first we designate as H, HA, HA is the head at A, which is only the potential head, because at A there is no velocity, no pressure, that we will come afterwards. Then when the fluid flows through this intake, there is a mechanical strainer, there is some loss at the inlet. When the fluid goes to B, therefore, there is a slight loss, small loss at the point B. That means, this loss, if you put like this, this is HB, this point, and this loss is given by H in, that is the head loss, frictional head loss, loss in the energy per unit weight in the intake, H in. Now, as the fluid flows from B to the point C, there is no other energy interactions with the outside, but there is again the head loss. That means, the energy is lost due to friction, and the mechanical energy is being converted to intermolecular energy, which we call as loss of energy per unit weight or head loss, frictional head loss from B to C. So, that the total head at C again drops from that at B. That means, this is the point C, where if we draw this, this part is our loss of head in friction in the inlet pipe. This we show as HF1. HF1 is the loss of head in the pipe, inlet pipe up to the inlet of the pump. Then at point C, the energy is added to the fluid gains head, and that is the objective of the pump. So, when fluid comes at D, the energy, total energy per unit weight or total head at D, that is HD, there is a sharp increase. So, from C we draw a curve like this, which goes here at D. This is the point D. This point D, which is our, if you just see, HD. Okay. Then at D, the fluid comes at a very high head, high energy per unit weight, high head, because of the head given to the fluid by the pump. Then as it flows from D to E, this point E is just at the outlet of the delivery pipe. All the points you must observe A is at the free surface of the sump, B is just after the inlet, C is just before the inlet to the pump, D is just at the outlet at the discharge end of the pump, E is at the outlet of the delivery pipe. So, head at D and head at E will differ by the frictional loss in the delivery pipe. So, therefore, if we just show this like this H E, then H D and H E, this difference is H F 2, that is the frictional head loss in the delivery pipe. Okay. Then from E to F, there is an loss known as exit loss. What is that physically? At E there is a velocity of discharge, that is a kinetic energy. When it is discharged into atmosphere, into the reservoir, then the fluid comes to rest. That means the entire kinetic energy at this discharge end is being lost, and this kinetic energy is lost. This is actually what happens, is degraded. There are formation of eddies and finally the liquid comes at rest. That means this kinetic energy actually is dissipated into the intermolecular energy, is converted into intermolecular energy, and this from the mechanical energy point of view we call as the loss of kinetic energy or the loss of kinetic head, and this is known as exit loss, and that we denote as H E. That means, if this is the final point F, F is this point just after the discharge, that means fluid at rest in the reservoir. So, if we take this one, then this part, that means E and F, H E minus H F is the H E. So, these are the therefore nomenclature. H F 1 is the friction in the inlet pipe, H F 2 is the friction in the delivery pipe, H in is the A to B loss, that is inlet loss, it is also due to friction, and ultimately H E from E to F, that is the exit loss, that is the loss of kinetic energy, which is designated as H E. Okay. Now, if we write certain equations, now if we denote the head at A is H A, total head at A, total head at A is what? Velocity, pressure is 0, because all pressure is expressed in terms of gauge pressure, that is the pressure above atmospheric. That means, the pressure head or the static head is the head above the atmospheric pressure head. The velocity is 0, so plus only this H A. H A, that means total head at A is H A. Now, if we write the total head at a free surface, total head at free surface of the, this is total head at A. Now, if I write the total head at free surface of the higher reservoir, or F, we consider F and total the free surface, this height is negligible at this, then we can write total head at free surface, total head sorry, at free surface of larger reservoir, of higher reservoir, not larger, I am sorry, higher reservoir is what? It is H S plus H A, H S plus H A, because here also similar way 0 plus 0, there is no pressure head, there is no velocity head, so H S, only the potential head. So, therefore, difference of these two, that means the total head between this point A and this point at the free surface of the higher reservoir is H S, and this difference, this H S is known as static lift or static head, or static head, means that the pump has to make this static lift of the water. Now, what is total head developed by the pump? Now, total head developed by the pump is different. Now, if we designate H 1 as the head at inlet to the pump, I am not writing everything, this is what? P 1 by rho g, pressure head, where P 1 is the pressure above the atmosphere at inlet, plus which can be read by a pressure gauge V1 square by 2G plus Z1, that is the potential head. Similarly, if we write H2, that is the head, total head at discharge end, that means just at discharge or outlet from the pump, as P2 by rho g plus V2 square by 2G plus Z2. Then the total head developed by the pump, total head developed by the pump, developed by the pump is H2 minus H1. Total head at outlet, total head at inlet. That is the total head developed by the pump, or sometimes we call net head developed by the pump. Total or net, whatever head developed by the pump is H2, and inlet head, outlet head minus A. And this is not equal to the static lift. That can be found out like this. If we want to find out the difference, this here itself I will do, the difference between the total head developed by the pump and the static lift, let us write the Bernoulli's equation between point A and C. If we write the Bernoulli's equation between point A and C, rather I should do this way, that if we write this here itself, I can write the Bernoulli's equation between point A and C, we write 0 plus H A, well, equals to, this is at A and at C, that means at inlet to the pump. If we write the modified Bernoulli's equation, that means in consideration of the viscous loss through the friction head loss, that means this will be P1 by rho g plus V1 square by 2G plus Z1 plus H in plus H F1. Well, and similarly, if I write the Bernoulli's equation between D and E, now here we can write one thing, that P1 by rho g, this can be written like that, plus V1 square by 2G plus Z1 equals to H A minus H in minus H F1. Now, similarly, if we write the Bernoulli's equation between the point D and F, final point, the fluid in the reservoir, liquid in the reservoir, water in the reservoir, then we can write P2 by rho g at the point D, the heads are like this, V2 square by 2G plus Z2, okay, equals to, here at this point or at the free surface, same thing, equals to all 0, free surface of that. So, we can write what? So, therefore, it is Z2 and the free surface it is HS plus HA, only elevation head. That means, one can write P2 by rho g plus V2 square by 2G plus Z2, that is the head here at D2, is equal to 0 pressure head, velocity head 0, only potential head. Now, this is the total head at the outlet of the machine, and this is the total head at inlet of the machine, which has been defined as H2 and H1. And the difference between the two is total or net head developed by the pump, H2 minus H1. So, if we subtract this one from this, we get H2 minus H1, H2 minus H1 from this equation. If you subtract this H2 minus H1, we get HS. Now, HA will cancel, plus here of course, I have done a mistake, the head loss in the pipeline HF2 has to be written, Bernoulli's equation 0 plus 0 HS plus HA, that means this is the total head plus the head loss due to friction in this pipe. So, Hs plus H in plus Hf1 plus He also loss Hf2 plus He. That means Hs plus sum of all the losses, sum of all the losses. Now, here again I repeat, there was a mistake that the Bernoulli's equation, if I write here the total head, total energy per unit weight P2 by rho g plus V2 square by 2g plus Z2, and here 0 plus Hs plus Ha is the potential head plus all the losses incurred or all the losses that has taken place in course of flow up to this point or the same thing. What is that? Hf2, the frictional loss in the delivery pipe, and He is the exit loss. That means exit loss. This is nothing but the kinetic energy loss, that is the kinetic energy, the discharge end. So, if you now subtract this H1 from H2, because this is H1, this is H2, you get this. So, here it is clearly seen that H2 minus H1, which is the net head developed by the pump, total or net head developed by the pump is H1 minus H2, H2 minus H1, sorry, that is the total head at outlet minus total head at inlet, becomes equal to static lift. What is static lift? Static lift is the vertical height of the free surface of the higher reservoir from the free surface of the lower reservoir, sum, plus all the losses. So, therefore, all the H due to losses. It is very clear from a common sense that a pump has to draw the liquid to have a static lift Hs, the liquid has to flow, and if liquid flows, it has to overcome all the resistance, flow resistance in the path. So, sum of this flow resistance in the path. So, therefore, it has to overcome, it has to spend energy to overcome the resistance, flow resistance, and that energy is known as energy lost or head loss, sum of all head losses. So, the pump has to deliver or pump has to gain that head, which is equal to the static lift plus all losses, that means the energy or head spent to overcome the flow resistance in the path. And here if we just separate this He, that means here if we could have written this equation instead of this point or F in at E, then instead of He we could have written V square by 2g. In that case, this is for your understanding, is Hs plus all the losses H in plus Hf1 plus Hf2 plus V is square by 2g. That means, if I keep it here, there is no reservoir, the water is discharged in the atmosphere. Then it can be interpreted that total head developed or the net head developed by the pump equal to the static lift plus all the frictional losses in the flow path. That means, the energy spent to overcome the flow resistance in the flow path plus the kinetic energy which is delivered at the outlet. This energy delivered at the outlet is also being developed by the pump. So, this is like this. But if we consider a reservoir where the fluid is at rest and final point is at the free surface of the reservoir or any point in the reservoir, then it becomes the total losses, because this becomes also a part of the losses that is known as exit loss, as you have read in fluid mechanics. So, therefore, this is static lift plus sum of all the losses. So, therefore, in this diagram we have been able to appreciate what the different terminologies like the head developed by the pump, the static lift, and how we can use the Bernoulli's equation to express this thing. Now, here this P1 by rho, total head developed here is this minus this. Therefore, we can write that total head or net head developed by the pump H is H1 minus H2 is P1 by rho g minus P2 by rho g plus V1 P2 by rho g, sorry this is mistake, H is equal to H2 minus H1. So, therefore, it is P2 by rho g, if you can write this way, minus P1 by rho g plus V2 square by 2g minus V1 square by 2g. It is just rearranged form. I am writing Z2 minus Z1. Now, in most of the cases, this diameter of the suction pipe or the inlet pipe and the delivery pipe is same, and for the same flow rate, volumetric flow rate, V2 and V1, these are cancelled. This is 0 because V1 equals to V2 equals to V1. But it is not always true. It may not be there if the diameters of the inlet and delivery pipe are different. So, in that case, this becomes P2 by rho g plus Z2 minus P1 by rho g plus Z1. So, this is nothing but the difference in piezometric pressure, which is being registered if we apply a manometer across this pump. And as you know, the manometer registers, that means if we apply a manometer here, that means here and here, if we apply a manometer, so the deflection, from the deflection of the manometer, let this is the deflection of the manometer delta H, this is the manometric fluid. So, manometer reads the difference in piezometric head. Sorry, this is will be an other way. I show you like this deflection, the fluid, this is pressure is high, this will be other way. So, that this is the interface, this is another interface of the manometric liquid. Usually mercury is used when water is the working fluid. So, therefore, a manometer attached between inlet and outlet, this you have already read in your fluid mechanics class, that this reads the piezometric pressure difference. And if we neglect Z2 minus Z1 is small compared to P2 minus P1 by rho g, you can neglect, and this becomes is equal to simply the piezometric pressure drop becomes equal to the simply static pressure drop or static head. So, therefore, we can find out this head developed approximately equal to that difference in the piezometric pressure head, which can be registered by a manometer. Manometer measures the piezometric pressure drop, P2 star minus P1 star. So, P2 star is P2 by rho g. P2 star actually is P2 plus rho g Z2. It cannot be written as P2 star. It is the piezometric pressure head. So, therefore, it can be written as P2 star by rho g minus P1 star by rho g. However, sense is the same. That is why this head is known as manometric head, because it can be found out by manometer, by the reading of the manometer. This is the piezometric pressure head. You remember, a piezometric pressure is defined as P plus rho g Z, where Z is the vertical elevation of the point where the static pressure is defined as P from a reference datum. That represents the piezometric pressure. If the 2 points are in the same horizontal line or horizontal plane, the Z will be same. So, the difference in piezometric pressure will be difference in static pressure. This is the piezometric pressure rate, piezometric. So, this becomes the difference in piezometric pressure rate, provided the velocities are same. And usually, in many of the cases, the inlet and outlet diameters of the pipe are same. That inlet diameters of inlet and delivery pipe are same. Okay, thank you.